This video will cover how to set up the lock-in configuration for the third generation of basic fiber photometry systems driven with the Neuroscience Console 500. Before diving into the software, we will quickly run over required background information. To skip this section, jump to the timestamps below. The fluorophores used for fiber photometry have specific excitation and fluorescent wavelengths which are important when setting up the lock-in configuration. Some fluorophores, such as GCamp, have an excitation wavelength that emits calcium-independent fluorescence. This wavelength is called the isobestic excitation and is commonly used to control for motion artifacts. It is also important to understand how the system is connected. In this example, the NC500 console is used to drive two Gen.3 minicubes connected to an assisted fiber optic rotary joint. This system will record a green and red indicator, GCamp and RCamp, from two different sites in a freely moving animal. Let's take a closer look at the NC500. The connections to minicube A are on the top row, while the ones for minicube B are on the bottom. The analog outputs are used to drive the LED excitations on both minicubes, with analog out 1 and 5 controlling the isobestic excitation, analog out 2 and 6 controlling the GCamp excitation, and analog out 3 and 7 controlling the RCamp excitation. In addition, the analog input ports receive photometry signals from both minicubes. Analog in 1 and 5 receives the combined isobestic and GCamp signals, while analog in 2 and 6 receives the RCamp signals. With a solid understanding of the system, we can open Doric Neuroscience Studio and the NC500 interface to configure the settings. To do so, navigate to the Live Processing tab, select Add Process, and then the Lock-in settings. This preset configuration will create both analog in and analog out channels required for fiber photometry. First, specify which analog input channel will be configured. Here, analog in 1. The saturation here depends on the type of detector, which for all IL-FMCs is the Doric detector. Next, use Add Channel to create the associated analog out, and use the Remove channel to delete the most recent addition. Since analog in 1 receives the combined isobestic and GCamp signals, it requires two analog output channels, one for each excitation. The reference frequencies specifies the sinusoidal frequencies that modulate the LED intensity and is used to demodulate the signal from the detector. As such, the reference frequencies of the analog output channels corresponding to the same analog inputs should never match. For the LED maximum current, use the IL-FMC Gen.3 mode, where 1 volt equals 100 microamperes of current. The output option specifies the type of output that will control the LED excitation power. The output level option uses a percentage of the LED maximum current to set the amount of excitation light delivered to the sample. Vmax is calculated automatically based on the LED power percentage, such that 100% equals 5 volts. Since the power output varies slightly between systems, you should, at a later time, measure individually the actual power of each LED to determine the mapping between the percentage of LED power and the measured microwatts. The target amount of microwatts must be determined by the user, since the value will depend on several external factors. A more direct way to set the LED excitation power is to use the optical power option, which is only available with the Pronto SI power meter. Here we can specify the output power at the sample for each LED in microwatts and compute the corresponding Vmax value during calibration. Make sure to specify the excitation wavelength, 4 or 5 in this case, before starting the calibration. If the specified power is too high, an error message will appear, while a successful calibration displays the updated Vmax. Note that a calibration must be done every time the power is changed. We recommend using half the power for the isobestic compared to GCamp to reduce photobleaching, regardless of the type of output option used. Lastly, the low-pass frequency value determines the bandwidth of the demodulated signal, and its sampling rate is 100 Hz, which effectively decimates the data by 100x, an optimization for fiber photometry. Select Add to create the first analog input and all its dependencies. The current configuration with one analog input channel would work for a simpler system recording GCamp at a single site. To add the RCamp signal at the same site, select the analog input 2 channel and the Doric detector. Use Add Channel to create analog output 3, which corresponds to 560 excitation. Now we will quickly set the unused frequency and the FMC Generation 3 mode. Again, the output power settings should be measured and set individually. This 2-input channel configuration would work for a system recording GCamp and RCamp at one site. Adding a second minikube for a second site is similar to what we've already done, but analog in and analog out numbers will be different. For instance, analog input 5 requires analog out 5 and 6, while analog input 6 requires only analog out 7. We've finished the lock-in configuration with 4 input channels for a GCamp and RCamp recording at 2 different sites. The live processing view contains a list of all the channels that we've created, including analog inputs, analog outputs, and demodulated channels. We can rename the channels using the username column, select which channel data will be saved in the data file, or use the config button to edit the power. In the experiment viewer, we can change the trace color or hide traces by disabling the channels. Select Saving Options to specify the file name and the saving path. Note that the data is saved in an HDF5-based .doric format, and we provide MATLAB, Python, and Octave codes to read these files. To save this configuration, including parameters, visualization details, and window display, select Save Configuration in the Channel List tab. After clearing the window, we can quickly re-import the settings using the Load Configuration button. Let's do a dry run to test the acquisition system. When optical fiber B is touched, the amplitude of the raw in white and the demodulated traces in purple, green, and red fluctuate only on the channels corresponding to minikube B. Note that when touching the fiber in ambient light, the amplitude of the raw trace diminishes because the total amount of light collected is reduced, whereas the amplitude of the demodulated traces increase since they are only picking up the endogenous fluorescence emitted by the skin. If the system worked as described, it can now be used with a test animal for experiment-specific optimizations. If you require further technical support, please reach out to us at support@doriclenses.com.